start solving problems. Okay, so to start with the session, so what is a gas turbine engine and what are the components of a gas turbine engine? So basically there are three main components. The first one is compressor, then the combustion chamber, third one is turbine, and also this turbine shaft is attached to the generator to produce electricity in case of it is a uh, uh, turbine gas turbine system. Okay, so basically air comes into the compressor at atmospheric pressure. It gets compressed, then it goes to the combustion chamber where the fuel is uh, injected to it or fuel is added. Then this fuel plus air mixture burns and expands at constant pressure in turbine. This expanded combustion products then discharge or rejected to the atmosphere. So basically a gas turbine engine works on a open cycle. Okay, that includes the uh, compression, combustion, and expansion, and then uh, exit to the atmosphere. So basically it is a open cycle. The first one is the reversible adiabatic compression, the first process. So it happens in the compressor, adiabatic compression. Then the second process is reversible constant pressure heat addition. So in the combustion chamber where the fuel is mixed with the air, the fuel and air mixture burns at constant pressure. Okay, then the third one comes is reversible adiabatic expansion, that happens in the turbine. Okay, so it consists of three processes and it is open cycle. So as you have already seen in uh, as you have already seen in the case of automotive engines, or we talked about automobiles, bus and trucks, all those things. So all those things, there is an internal combustion engine, and internal combustion engine also works on an open cycle. Okay, but you know to uh, ease of study or ease of understanding, we consider all those cycles as closed cycle. And similarly here in the gas turbine engines we consider a closed cycle by adding one more process, that is a reversible adiabatic no sorry that is a reversible constant pressure heat rejection to the atmosphere. Okay, so with the addition of an extra process at the end, it becomes a closed cycle, that is a Brayton cycle. So basically Brayton cycle consists of two reversible adiabatic processes and two reversible constant pressure processes. And now if you remember in the previous lectures, the initial lectures, we also talked about the Rankine cycle. Here we are talking about Brayton cycle. So both in the Brayton cycle and Rankine cycle, there are two adiabatic reversible adiabatic processes and two reversible constant pressure processes. Okay, so what is the difference? So question here comes, what is the difference between both these? Okay, now uh, to look at the differences between both Brayton cycle and Rankine cycle, let us look at this diagram. Okay, so as you remember, this diagram is between T and S, entropy and temperature diagram. Here here you see this from point 1 2 3 and 4. This is a typical Rankine cycle, and adding a Brayton cycle to this diagram, this A, B, C and D is the Brayton cycle. So what happens in a Rankine cycle is, in the Rankine cycle the working fluid we are using is uh, like this working fluid goes in a phase change. So sometimes like in point 3 and 4 it is a pure liquid. In some time it is a, in vapor form, and sometime it is in gas form, okay, in superheated state. So in a Rankine cycle, that also consists of two reversible adiabatic and two reversible constant pressure processes, the working fluid goes in phase change, okay. But in the case of Brayton cycle, the working fluid is always in gaseous form and doesn't go into the phase change, okay. So that is the main difference, and from this figure you can see it clearly that the Brayton cycle always works in the gaseous phase, and Rankine cycle works in a area where the phase change occurs, okay. So that is the basic difference between Rankine and Brayton cycle. uh, and also when we saw this that Brayton cycle always works in the gaseous phase, so that time the compression work in case of Brayton cycle is, you know is of considerable amount compared to the turbine work. But in the case of Rankine cycle, the compression work from point 3 to 4 is very less compared to the work achieved from the turbine from point 1 to point 2, okay. So that's why these, Rankine cycle or vapor cycle uh, engines are, or systems are more popular compared to the Brayton cycle in power plant, okay. Now let's move to the next part, that is the, like how a Brayton cycle looks on PV or NTS diagram. So basically Brayton cycle consists of adiabatic compression, that is from point 1 to 2, then constant pressure heat addition, that is from point 2 to 3, then again adiabatic expansion in the turbine from point 3 to 4, and again constant pressure heat rejection, that is from point 4 to 1, and that also can be seen on TS diagram, okay. And if we calculate the efficiency of this Brayton cycle, that comes as 1 minus 1 upon Rp raised to power gamma minus 1 upon gamma, and here Rp is the pressure ratio, okay. Here Rp is the pressure ratio, and pressure ratio is P2 by P1. Here this pressure by this pressure, that is P2 by P1, okay. Now as we know the frequency, the efficiency of this Brayton cycle, the efficiency is solely depend on the pressure ratio Rp, and Rp is also, directly connected to the temperature ratio as well, okay. So now as you can see in the formula of efficiency, if we increase the pressure ratio Rp, the cycle efficiency will also increase, okay. But what is the limit for Rp? Can we increase it to infinite values? Let us see in the next slide. So you know pressure ratio we can vary, but we have an upper limit for temperature that can, that can be uh, bear by the material we are using for the engine, okay. So in the case of, you know turbine engines, they work continuously, they work on like steady flow, so they are always subjected to the high temperature, the highest temperature we can achieve, okay. So for that case, it the temperature limit is there, so almost 800 degrees centigrade for normal engines, and for almost 1000 degrees centigrade for, uh, you know those engines which are being externally cooled, okay. So there is a temperature limit, so we cannot go above that temperature. So let's see, let's assume like we have already fixed the maximum temperature T max, the T minimum temperature is the atmospheric temperature, the T minimum. So let's see in this figure we have set these T max and T minimum here. Now we can set the pressure ratio, okay. So now let's see the in the first case we have a pressure ratio. We are going from point 1 to point 2. So we have a pressure ratio of P2 by P1. In that case, you can see this lower figure here. So it is like initial cycle. So we have some work input and also we have some efficiency for this pressure ratio. Now let's we increase the pressure ratio from point to 2 to 2 double dash. So once we increase this pressure ratio from point 1 to 2 double dash, we can see the work obtained is increased and also the efficiency is also increased because we are increasing the pressure ratio. Now if we increase the pressure ratio further and go up to point 2 dash, we can see that when we go from point 1 to 2 dash, the work obtained is also reducing. The efficiency is increasing but work obtained is also reducing. So from here we can say that as we increase the pressure ratio, the efficiency is always increasing, but at after some point the work achieved or work done starts reducing. Okay, so uh, so the maximum pressure ratio RP we can get is T max by T minima raised to power gamma by gamma minus 1. That is the RP, the maximum pressure ratio. But at this maximum pressure ratio, the work achieved is 0. Okay, so you can see in the lower left diagram. So at this pressure RP max, the work achieved is 0. So what is the use of a cycle or engine which has a very high efficiency but no work output? So that engine is of no use. So we want to achieve a balance between the efficiency and work so that we can get benefit of this high pressure ratio as well as we can get the maximum work output. Okay, so in the lower left figure you can see if we increase the pressure ratio at till some point the work also increases, and at a point the work done is maximum. After that the work done is start coming down. So we want to know this point, this pressure ratio at which the work achieved is maximum, and this pressure ratio, the optimum pressure ratio, is defined as T max by T minima raised to power gamma by 2 gamma minus 1. And if you see both this RP max and RP optimum, you can see that RP optimum is nothing but the root of RP max. Okay, yeah. So this is the optimum pressure ratio for maximum work output. Now what is the maximum work output? So corresponding to this optimum pressure ratio, the maximum work output is mcp T max root minus T min root raised to power 2. Okay, so this is the maximum work that can be achieved from a turbine engine working between two fixed temperatures T max and T minimum. Okay, yeah. So this is basic about the turbine engine and Brayton cycle. The engines also have sometimes they use intercooling, reheating and regeneration as well, similar to the Rankine cycle or steam power engines. So similarly, intercooling occurs between you know between low pressure compression and high pressure compressor. This is where the intercooling is applied. The reheating is applied between low pressure turbine and high pressure turbines. Okay, and regeneration occurs, uh, to use the exhaust heat to, you know to raise the temperature of the air that is coming from compressor and going to the turbine. Okay, here the regeneration occur. Okay, so in the case of regenerator, efficiency always increases, but work done doesn't change. Okay, so there is no change in work done, but efficiency always increase with the use of regenerator. But in the case of intercooler and reheater, in both the cases, work always increases and efficiency always decreases. So it is always useful to use intercooler or reheater in combination with the regenerator to have that combined effect of increased efficiency as well increased work output. Okay, so these intercooler or reheater are never used without the regenerator. So this was the basics of this, this gas turbine engines, this Brayton cycle, and the use of intercooler, reheater, and regenerator. Now we will look at the questions based on these concepts, and we'll try to understand, and we'll solve them. Okay, so let's move to the first question. So here is the first question. In a single stage open cycle gas turbine, the mass flow through the turbine is higher than the mass flow through the compressor, because, so what happens here is, here is a compressor, air comes from here, this goes to the combustion chamber. Okay, from here it goes to the turbine and air gets out. Okay, so what happens here is, here goes air, but in the combustion chamber fuel is also added, and this air fuel mixture gets burned, and this burned mixture goes from the turbine. Okay, so in the combustion chamber we are adding extra fuel to the air. So that's why if we have a mass m a here, we will have a mass m a plus m f, that is the mass of fuel plus air. So that's why the combustion products going through the turbine have a more mass flow rate than the uh, flow through the compressor. Okay, so let's check the options. The specific volume of air increases by use of intercoolers, so that doesn't change the mass flow rate. The temperature of air increases in the reheater, that also doesn't have any effect on mass flow rate. The combustion of the fuel takes place in the combustion chamber. Yes, so in the combustion chamber, combustion of fuel takes place plus fuel is also added, so the mass flow rate is higher in the turbine. And the specific heats at constant pressure, for that also doesn't have any effect on this. Okay, yeah, so any doubt here? Now let's move to the next problem. So here is the next problem. So yeah, so a gas turbine plant operating on Brayton cycle has maximum and minimum temperatures at 800 degrees centigrade and 40 degrees centigrade respectively. Okay, calculate optimum specific work done by the gas. Okay, so here we are given T max, that is 800 degrees centigrade or 1073 Kelvin, and also we are given T minimum, that is 40 degrees centigrade or 313 Kelvin. Okay, and we are asked calculate optimum specific work done. So as we saw in the last few slides that optimum work is at rp optimum, and this rp optimum, the total work done is this mcp, uh, t max root minus t mini root raised to power 2. Okay, this is the uh, optimum work we achieved at for like optimum pressure ratio. Okay, so now it is asked that optimum specific work done by the gas. So when it is asked as specific work done, that means question is asked for unit mass flow. Okay, so the work specific work is cp root of t max minus root of t minimum whole square, and that is, and what is the cp of air? The cp of air is 1 kilojoule per kelvin. Okay, so 1 into root of 1073 minus root of 313 raised to power 2. Okay, so when we solve this, the value comes nearly 228 kilojoule per kg. Okay, so this is the answer. So in the options we can check 150 no, 330 no, 400 no, but 228.3 is the option. So it is the correct option. Okay, so this is the optimum specific work done by the Brayton cycle working between 800 degrees centigrade and 40 degrees centigrade temperatures. Okay, let's move to the next problem. Now, so the next problem is at high subsonic speeds, a propulsive jet of smaller mass flow but higher velocity is achieved by a turbofan or bypass engine. Okay, so here it is being asked about turbofan engine, that is also called as bypass engine. So let's see how this engine looks like. Okay, so this is the turbofan engine or bypass engine. So what happens in this engine is, so this is a fan here. This fan pushes some air into the engine. So the some part of this air goes to the compressor here, and some part goes from this duct. Okay, that is around the compressor and turbine. Now what happens is, some part going into compression and some part going around it. So the part going into compression is being compressed, then fuel is added in the combustion chamber, the combustion happens, then the expansion of the combustion product happens in the turbines, and this combustion products come out from the nozzle. So what happens here is, the air that is being forced into the duct, that also comes out from here, and this air add with this combustion product exit from the nozzle, and these both the products mix together and results in a high velocity propulsive jet. Okay, so this is the principle of turbofan engine. And bypass engine, it is called as bypass engine because the some fraction of air is being bypassed through this duct, and some air is going through this whole engine assembly, including compressors and turbines. Okay, so yes, in the case of turbofan engines, a propulsive jet of a small mass flow but high velocity is achieved because this extra air that is coming from the duct mixed with the combustion products coming from the nozzle and results in a high velocity propulsive jet. Okay, so this is a true statement. Yes, this happens. Let's move to the next problem. So the next problem is the Brayton cycle, which is used in aircraft automotive engines, is a closed cycle, open cycle, either closed or open cycle, or cannot. So we have already talked about it. Brayton cycle is an open cycle that is used in the aircraft or automotive. Okay, but for the sake of simplicity and sake of analysis, we add an extra process, that is constant pressure heat rejection, and we analyze it as a closed cycle. But yes, the cycle used in aircraft and automotive is an open cycle. So this is the correct option. Let's move to the next problem. Yeah, so the next problem is a heat exchanger can be used only if there is sufficient large temperature difference between gases leaving the turbine and air leaving the compressor. Okay, otherwise it will incur additional capital cost and maintenance requirement. Now, as you remember, the you know heat exchanger or regenerator, in regenerative cycles, the heat exchanger is always added between this let me so here the combustion chamber, the compressor, the turbine, and then this goes to there. Okay, yeah, so this is the heat exchanger. So as we know, the heat exchanger in regenerative cycles is added to to heat this air that is coming out of compressor with the help of the heat in the exhaust of turbine. Okay, this is where the heat exchangers are used for in regenerative cycles. Now, if the temperature of gases leaving the turbine, so that is the temperature at point 4 here. Okay, and the air leaving the compressor is having a temperature at 2. Okay, so if there is not a big difference, as we know that this Brayton cycle always work in gaseous state, so it is always desirable to have a large difference between point 2, that is the gases leaving the air compressor, and point 4, that is the gases leaving at the turbine. There should be a sufficient temperature difference, then only we will get this you know amount of heat, the good amount of heat that will be beneficial. Otherwise, the adding a heat exchanger, those accessories and all those things, that will result in increased cost, and also the more component, the more accessories we use, more maintenance we need. Okay, so it is always desirable to have a large difference between point 2 and point 4 temperature, then only we can afford a heat exchanger, otherwise no. So for this question, yeah, it is right that there should be sufficiently large temperature difference, then only heat exchanger is advisable, otherwise it is not a good option for our you know whole gas turbine system. So this is also true. Okay, yeah, so this next problem here is, which of the parameters are of importance with respect to performance of an ideal cycle gas power plant? Okay, So whenever we discuss you know whenever we analyze a cycle, we always focus on work done or efficiency. Okay, and both the work done and efficiency are directly related to the fuel consumption. Okay, so the total work done we are always concerned about, so this option is right. The efficiency, we always talked about the efficiency, like efficiency is 1 minus 1 by r raised to power gamma minus 1 upon gamma. Okay, so we are always concerned about the efficiency. And also specific fuel consumption. So specific fuel consumption is nothing more but work received per unit mass of fuel. Okay, this is this. So yes, uh, the important parameters of any cycle, they are work output, efficiency, and specific fuel consumption. Yes. So all the three options are correct here. All those three, work output, efficiency, and specific fuel consumption, all three are important parameters whenever we analyze a cycle. Either it is a gas power cycle or in an auto cycle or diesel cycle. Okay. Now the next question is, the power output of an ideal gas turbine cycle is a function of. So here power means the work. Okay, so they are talking about work. Yeah, so you know the work W is given by Cp, the temperature T4 minus T3. So first see the cycle. Okay, so it is TS diagram. Here the cycle is working between this 1, point 2, point 3, and point 4. Here is the heat addition, here is the heat rejection, here is the work done. Okay, so the work output or power output W is Cp, heat added is Q1, that is T3 minus T2, minus the heat rejected, that is T4 minus T1. Okay, yeah. So the power output, and this we also looked upon the optimum work output as well. So all this power output, they depend on temperature. Okay, as well as this temperature with the with this temperature limitations, we also this temperature limitation also affect the pressure ratio as well. Okay, so pressure ratio is also not independent, it is also a dependent parameter here. So basically the work output or power output basically depends on temperature as well as pressure ratio, because both are not independent to each other. Okay, so here the pressure ratio, it is depends, the temperature ratio is, it depends. So it depends on both the pressure ratio and the temperature ratio, but not only the pressure ratio, temperature ratio. Okay, so a power output of a gas turbine cycle depends on pressure ratio as well as temperature ratio. Okay, it is not a function of only pressure ratio or only temperature ratio, but the function of both pressure ratio as well as temperature ratio. Okay, yeah. So the third option is the correct option. Here the next problem is the multi-stage compression with intercooling and multi-stage expansion with reheating in a gas power plant is intended for improving. Okay, so as we already discussed, in the case of intercooling as well in the case of reheating, both of these results in increased work output and decreased efficiency. Okay, these both result in increased work output and decreased efficiency, and when this intercooling or reheating are used in combination with regeneration, then these results in definitely increased work output, but increase or increase or constant efficiency. Okay, so efficiency may increase or not with the combination of intercooling, reheating and regeneration, but if we are using intercooling and reheating only, the work output increases but efficiency decreases. Okay, so here in the question it is asked that multi-stage intercooling and expansion with reheating in a gas power plant is intended for improving. So these intercooling and reheating always results in higher work output. Okay, so that is the only intention to use these things. So here we can see the cycle efficiency, no, it always decrease. Power output, yes, both power output and efficiency, no, none of these. So this is the right option. So multi-stage compression and multi-stage expansion with intercooling and reheating respectively results in higher output, higher power output, but lower cycle efficiency. Okay, so the second one is the right option. Let's move to the next question. So here is the next problem: intercooling in gas turbines. So what happens with the intercooling? Decreases net output but increases thermal efficiency? No, it is the wrong option, because output always increases and efficiency always decreases. So the first one is the wrong option. Increases net output, that is right. Decreases thermal efficiency, that is right. So second option is correct. Decrease both net output, galat. Increase both net output and thermal efficiency, this is also wrong. Okay, the second option is correct. With the intercooling, net output is increased but thermal efficiency always decreases. Okay, any doubt here? So yeah, to the next and last question. In gas turbine, intercooler is placed in between high pressure compressor and turbine? No. Okay, so as you remember, intercooler is always placed between low pressure compressor and high pressure compressor. Okay, and reheater reheater is always placed between high pressure and low pressure, high pressure turbine and low pressure turbine. Okay, and heat exchanger for regeneration. It is always added between high pressure compressor and high pressure turbine. Okay, so here in the question it is asked, in gas turbine intercooler is placed in between high pressure compressor and turbine. No, intercooler is always placed between low pressure compression and high pressure compression. Between high pressure compressor and turbine is added as a regenerative heat exchanger. Okay, so in this question this statement is false. The intercooler is connected between low and high pressure compressors, and between high pressure compressor and turbine is attached as a regenerative heat exchanger. Okay, so this statement is false. So if you have any doubt till here, you can ask. Okay, so this is like this session was like very basic concepts to the efficiency and all those things. If you have any doubt, you can ask. Okay, no doubt. So we can close this session here only and see you guys in the next session.